Beck at NASA Goddard Space Flight Center, and today I'm happy to introduce Dr. Paul O'Brien as our speaker. Dr. O'Brien is a research scientist in the Space Sciences Department at the Aerospace Corporation. He holds a BA degree in Physics and Classics from Rice University, and MS and doctoral degrees in Earth and Space Sciences from the University of California in Los Angeles. He has over 25 years of experience in space science and the effects of the charged particle environment on space systems. His research experience includes magnetospheric physics with special emphasis on radiation belts and the empirical analysis of in situ particle data. He is one of the lead developers of the AE9, AP9 IRENE radiation specification models and the Spacecraft Environmental Anomalies Expert System. He's a past chair of the COSPAR panel on radiation belt environment modeling, and he's the editor of the journal Space Weather. Before we begin, I'd like to remind you to keep your microphones on mute, post any questions that you have in the chat box, and then I will ask them for you at the end of the seminar. This is being recorded, and it will ultimately be posted on YouTube. And finally, I'd like to say one of the things I most admire about Paul is his willingness to ask questions. So I'd like to encourage, especially early career people, to ask questions. Don't be shy to ask questions. Please go right ahead. And I know Paul will enjoy answering them at the end. With that, Paul, please go ahead.
Okay, thank you, Dave. That was a very nice introduction. I should tell you, this is a talk based on a recently published paper in JGR, and the co-authors of that paper were Janet Green, Alexa Halford, Betty Kwan, Seth Claude Pierre, and Louis Ozeki. And there's a link for the paper down there at the bottom. Well, advance. There we go. Okay, so the outline of this talk is I will give a little bit of background on radial transport and drift phase structures, which are critical to the analysis that we'll be doing. And sort of the central thing is relating the drift phase structures to diffusion coefficients for radial diffusion coefficients. And then we'll do an event study looking at 3 different events to compare climatological diffusion coefficients to the drift phase structures that we see. The goal of that being to determine whether quasi-linear radial diffusion, which is a widely used modeling framework, is appropriate for individual storms. Now, not every storm has them, but we also can look a little deeper and look at event-specific diffusion coefficients. And then we'll wrap up and talk about some future work. I'd like to thank Scott Elkington as well. He provided this nice animation and some of the graphics in the next few slides. So when we talk about transport of energetic electrons in the radiation belt, we usually talk about some kind of drift resonance with ultra low frequency or millihertz waves. And for that to work, a resonance, as always, sort of requires some relationship between the particle's periodic motion, in this case the drift period, and the wave period. And as illustrated in this, with this little particle going around the Earth, if the wave is oscillating at the same frequency that the particle is drifting around, then the particle will find itself preferentially in the part of the wave that would accelerate the particle at different times through its orbit. And that's kind of depicted over here on the left with the electric field and the particle velocity. And when you sort of do the dot product of those, you're constantly adding energy. And you can write this out explicitly in an equation for the change in energy. But for particles that don't have the right frequency, their velocity goes through its 2 pi cycle, while the wave electric field might go through many cycles or just simply be misaligned. And that leads to both energy loss and energy increase over the course of the drift orbit, and those particles tend not to gain very much energy. So this is essentially what one of the things we're going to be looking at here is this resonance picture on the left correct, or is there something else going on? Okay, so what happens when you have a single idealized wave is that the particle gets trapped in an island, and these figures here all show the energy of the particle versus the wave phase. And so the wave accelerates the particle for part or all of the wave cycle, and the particle actually kind of gets trapped in the wave. It's sort of like surfing the wave. But if you add multiple waves, if you just have a couple, or if they're far enough apart, then you can still have islands, but you'll also get these diffusive regions. These are Poincare cross sections showing where particles are over the course of time. And these islands can either, you can have several different islands if you have a multiple monochromatic waves superimposed on each other, or if they are very closely spaced or effectively broadband, then you can just kind of have a sea of diffusion where particles interact somewhat randomly with the waves. And that isn't required for quasi-linear diffusion, but it is sort of the best picture of quasi-linear diffusion because it gives you this sense of that there's kind of a continuous series of small kicks going to the particle, which can cause it to increase or decrease in energy. And there's some phase dependence on how all these things work, depending on where the particle is in relation to the wave phase. It's either being accelerated or decelerated. What we see in space is sometimes monochromatic waves. There have been a few very nice examples published in the literature, but most of the time we see something that's at least multiple frequencies or maybe fully broadband. And so that gives us a window to have more like quasi-linear diffusion. I'll explain over the next few slides what we really think are the criteria for quasi-linear diffusion. But let me first cover the opposite end of things, which is advection or impulses or transit time resonances. There are other ways waves can interact with particles. A classic example is the March 91 event, where essentially a soliton passed through the magnetosphere and left behind accelerated radiation belts. And the particles that happened to be in phase with that during their transit through the radiation belts gained a lot of energy, while others lost, some gained, some lost. And this produced a substantial amount of drift phase structure. So in these spiky plots here, we have sensors on the CREST spacecraft making electron measurements, and the initial impulse passes by and the particle flux goes way up. And these are very large energies, 6 MeV and above. And then when the particles come back around the Earth, there's a little bit of drift dispersion, but you can still see the spikes, and then you get drift dispersion again, and after 3 or 4 wave periods, there's been enough drift dispersion that you can't really make out those drift echoes anymore. And this has been very well represented by simulations. This one by Xinlin Li, and that's sort of the picture of a soliton. But you can also get something like that when you only have partial, you have a resonance, when the wave is present only over part of a drift period. And so if the waves are traveling waves, for example, then they might only interact with a particle briefly. And while this signature, this soliton, is not a traveling wave, it is a traveling soliton, the particle can't tell the difference between those two phenomena. Now, generally, this is not a wildly efficient process, but it is certainly a way that waves can interact with particles and push them around, change their energy, or change their, when you change the energy of a particle, you typically also change its radial position a little bit. Another picture is sort of electrostatic pulses. Rather than being electromagnetic waves. So this is a picture from a paper by Margaret Shen. And the superposition of many of those can lead to something like diffusion on a storm-by-storm basis, but it doesn't work very well when the particle drift period the particle doesn't go through many drift periods in the course of a storm. And so at lower energies, that tends to not be a very good description. So when you look at things like ring current models, the number of drift periods during the main phase can only be 4 or 5, and so you don't tend to always get into the diffusive regime. But at radiation belt energies, you should. However, several simulation studies of the radiation belt particles have shown that individual storms really look very different from each other, even though they may be driven by the same nominal diffusion coefficients. And so this is an example on the right where you see all these thin gray traces. That's the outcome of the L displacement, or the amount of radial transport as a function of time for individual storms. And then when you average over all the storms, you get this kind of wiggly dotted line, and it falls very close to what you would expect for the average diffusion coefficient. The issue is, of course, that we really do use 3D diffusion codes to represent radial transport and other kinds of transport in the outer belt, and it is able to agree with data quite well. And so we have sort of a conundrum of, what's going on? Why are we not able to? Why are the simulations and why are some simulations in disagreement with other simulations and the data? And so I should mention Sasha Yukorsky did a lot of good work on this over the past 10, 15 years. So back to my central question, is quasi-linear radial diffusion an appropriate framework for individual storms? It's certainly used that way in our common practice, but it isn't necessarily clear that that's the right approach. So let me tell you what we're going to do here. Quasi-linear theory assumes a superposition of many small random perturbations drawn from a distribution that is quantified by a diffusion coefficient. That is essentially the single number you need to describe quasi-linear diffusion. It can also include an advective motion, which would be deterministic, or it's the mean of that distribution. That's not always included in every model, but it certainly is possible to have it. And the advective mean can be thought of like that March 91 event. A whole bunch of particles are all getting transported in the same direction, and it doesn't happen over and over again, so that it doesn't ever average out. Having increases and decreases in energy doesn't average out. For those of you who like to think in terms of statistics, the reason that you can get away with just having sort of the mean and the variance, the diffusion coefficient is kind of the variance of that distribution. The reason you get away with that is the same reason that when you add many variables together of almost any kind, they give you back a Gaussian distribution. That's called the central limit theorem. But there are some cases where that kind of central limit theorem approach doesn't work. If there are very few perturbations, which is the case that Margaret Chen was talking about, or if the distribution of perturbations has a sufficiently fat tail, and I think this is where Sasha Yukorsky's work has tended to focus, then if either of those happens, then the quasi-linear approximation will break down. There isn't enough randomness, or the randomness has such a fat tail to the distribution that it can't converge to this Gaussian type shape. And if that doesn't happen, then quasi-linear theory doesn't really work. But all of these mechanisms that perturb the radial position of particles leads to drift phase structure. And I'll show a little picture of that in a later slide. And that drift phase structure should be in excess of what is expected from quasi-linear theory diffusion coefficients. And so what we're looking for is large drift phase structures. How common are they in the data? And we have to define what large is, because there's always some drift phase structure. And so we estimate the size of that based on the quasi-linear diffusion coefficient itself. And I should note that the quasi-linear diffusion coefficients are typically derived from electromagnetic measurements, not particle data. So they're pretty much an independent measure. The other thing we need is local particle phase space density gradients. And that we have to get from in situ data as well. Once we have all that, we basically can look at the size of the drift phase structure and compare it to what quasi-linear theory would accept. Anything within the bounds of quasi-linear theory would be okay, but if the drift phase structure is larger than that, then it isn't okay. All right, so how do we get to this point of having drift phase structure from radial transport? In this cartoon, in black, we have the pre-existing phase space density before a transport event occurs. And this is a nice smooth radial gradient. It can be inward or outward. In this case, we've chosen to say that there's more phase space density at high L, which is pretty much usually the case in the quiet radiation belts anyway. And then if you imagine a perturbation where you change the L value of the particles, at different local times get a different perturbation to that L value, what's actually happening is that they're being transported to a different L. But there's a phase-dependent L transport. And so you get more phase space density for the particles that were moved inward and less phase space density from the particles that were moved outward. And this spread of phase-space density is phase angle dependent or azimuthally dependent. And if you're a satellite sitting still, that structure drifts past you and you see it as drift phase structure. Now, on the right-hand side, I've given you some of the equations and things that are going on here. The net diffusion in this case, or the net transport in this case, is 0 if you just averaged over the delta L's. But when you weight it by phase-space density, it produces actual transport. We represent this with a diffusion coefficient, which is this quantity here. It's the average of the square of the change in L divided by 2 times the time scale. And we can relate that DLL to the variance over a drift orbit of the log phase-space density. There are other ways you could approach it, but we use log phase-space density because we usually work in logs in the radiation belts anyway. And so if you think about the log, the drift phase structure is measured by the square of the change in the log phase-space density averaged over a drift. Then you can relate that back to the diffusion coefficient. You need 2 things. You need the how much variation there is in L, and we'll pull that out of the DLL equation itself. And then you also need a phase-space density gradient. How steep is this black curve? When you put that together, that can tell you, that can relate the amount of phase-space density structure you see, which is sort of how big is this spread in the picture, the vertical spread in the picture, related back to the gradient and how large DLL is. Now, we can do this for quasi-linear theory as sort of our null hypothesis and see what it would predict in terms of drift phase structure and compare that to what we see on orbit. But of course, because I'm giving this, we're going to have some equations. So I'm just repeating the equation from the previous step. I wanted to tell you that we're getting our DLL values from the Ozeki and Mann work, the climatological model from a 2014 paper, and the event-specific calculation has been presented in several papers by Mann and Ozeki. We have to figure out what delta T is in the equation, and for that we choose the drift period. So we will be subtracting off drift average flux or drift average phase-space density to obtain the delta F. And we're going to look for times when this change in the log phase-space density is larger than the gradient of the phase-space density with L times the square root of 2 tau. This is the equation up here with its square root around it. So that's where that all comes from. And I'll note that this is the gradient of the log of the phase-space density gives you the size of the change in the log phase-space density. So we're looking for when these things happen, when these large drift phase structures happen, we know we're not in the quasi-linear regime. We can't observe this delta LNF, the delta log phase-space density directly. We compute it by detrending the observed phase-space density. And because flux and phase-space density are related by the square of the momentum and the momentum's not changing, we can talk, or it's not, the momentum does change. We have that on the sensor. So we can relate the change in log phase-space density to the change in flux. So J is flux, F is phase-space density. And so we can observe the change in the log flux much more easily than we can in the log phase-space density. And so that we've just basically written the same formula from before where we have log flux on the left side, but I note that we still use the phase-space density gradient. You can't get away from that part of the problem. And that's a little trickier to compute. So let me show you how we do that. I promise this won't just be all equations. The drift average phase-space density, which has got this bar over it here in these equations, it can be related to the gradient of the drift average phase-space density in momentum, pitch angle, and time can be related to the gradient of the drift average. Let me say this again. This equation's ugly. I'm going to get it wrong here. The gradient in drift average flux with respect to momentum, pitch angle, and time can be related to the gradient in drift average phase-space density with respect to M, K, and L, the 3 adiabatic invariants. And you'll note here in these derivatives, we're taking the derivatives of flux with fixed pitch angle, momentum, or time. We're taking the gradients of phase-space density with fixed M, K, or L. And this red parameter is the one we want. In order to relate these to each other, this is basically a change of variables from one coordinate system to another. And so there's this matrix that does the conversion. We get some of the parameters from simple analytical formulas, but most of them come from the magnetic ephemeris of the satellite. And we're going to be using the Van Allen probe's RBSPB satellite. This is a general approach that could work for other, computing phase space density and other phase space density gradients in other contexts. I should note that there's a -2 here because of the conversion between phase space density and flux. So we're going to obtain these derivatives from magnetic ephemeris and from analytical formulas. We observe the gradients of the drift averaged flux with respect to momentum, pitch angle, and time at fixed momentum, pitch angle, and time. I'll note that this, for example, to compute this derivative, you have to look at 2 or 3 different energy channels and compute a derivative of the flux with respect to energy. Same thing for this. For pitch angle derivative, you have to look at several different pitch angles. The Van Allen probe's MagEyes data is very nice for that because every minute or so it produces a spectrum as a function of energy and pitch angle. And of course, you have to look along the orbit track to look for changes over time. And this is all done in the drift averaged flux. So we'll actually have to average the flux in time before we can compute those derivatives. So I mentioned that this is the MagEyes data. We look at 4 different energies in this study. There are 2 different kinds of MagEyes fluxes. Most of you are probably familiar with the main rates, which are fairly narrow energy bandwidths of sort of 30% or less. And that also translates to how much uncertainty there is in the drift time in any particular measurement that you make. And then there's also these histogram channels, which are much narrower, and they're built out of the same physical sensor, but their data are processed in a different way to obtain a narrower energy bandwidth. And this energy bandwidth is important because it tells you the spread of drift times for any particular particle as you move, and it depends on where you are in the magnetic field. But the particles we're talking about all have drift periods of 30 minutes or less. And the histogram channel that we're interested in is embedded here in the main rate for the 1 MeV channel that we're looking at. So 1 MeV is kind of where we're going to do our focused work. And as I mentioned, we're using RBSPB or Van Allen probe B. So I have several plots that are all in the same format. I want to show you how they kind of introduce them to you before we use a bunch of them. The first kind of plot is just an overview of the Van Allen probe's mission. It's a time series of several parameters that we think are important: IMF, BZ, solar wind speed, pressure, and then we have the 3 or 4 fluxes. Now, the first event, we don't have the lowest. We don't have one of the flux channels, and so in this case, we only have 3 fluxes plotted versus time, and the satellites are moving in L, and that L value is plotted here in the second to last panel. And we've color-coded inbound and outbound so that when the satellite is outbound, or we've shaded it, so when the satellite is outbound, you'll have a gray shading background, and when it's inbound, you have a white shading background. And so that gives rise to this sort of M-shaped structure of the radiation belts. And that's just passing in and out of the belts. In the first storm, we have a pretty large negative BZ. We have a slowly increasing solar wind speed. There is a pressure increase at the beginning of the storm that then kind of drains off slowly. And then DST gets down to about -130, and KP gets up to about 6. So this is a moderate to, it's not a huge storm or anything, but it's a moderate storm. And the other thing we should look at here during this storm is that we have fairly elevated electron fluxes, and then when the storm comes along, they drop out and then they rebuild over time. Some of that is the natural DST effect that we're all familiar with, where it's an adiabatic effect of the changing magnetic field topology, but some of it is a genuine change in the particle fluxes. And what we see is that by the end of the storm, we have a different configuration of particle fluxes, and the highest energies have not recovered. Although they do increase compared to their lowest values during the main phase of the storm. And these little A, B, C, D markings are important. They are the individual passes that we're going to focus on during this storm. Now, an individual pass has a lot of stuff going on in it. So let's walk slowly through this. Maybe we should start on the right-hand side. On the right-hand side, we have the particle flux as a function of L. But we've got three different bold curves: the previous pass, the current pass we're looking at, and the next pass. And this is for the 1 MeV channel. That same data are plotted in a detrended form where we've removed the drift average component in the top panel here. And you can see there's some data dropouts. And the color coding is the same as on the previous slide and indicated here. So the fluxes are detrended. So what we're seeing is basically the residual drift phase structure when you're removing 30-minute time scale average fluxes. That's not exactly the drift period, but all the drift periods are shorter than that. And so there could be still some small trending and things that are inside that we would still pick up. But in fact, we don't. There are 4 plots here, or 3 plots in this case, of different colors that are thick. And then there's a thin magenta line, which is the histogram channel at the same energy as the orange main channel. We've got some L values marked. And there's also a region that we mark where the vehicle is moving too fast in L. Its dL by dt is too large for us to consider the results very reliable. And we've marked that here in the time series and also marked it over on the L time series, the L plot. Now in the bottom panel, we have several different things going on. First, we have the detrended 1 MeV flux, both main channel and histogram channel. Those are plotted in orange and magenta again. And then we have a detrended magnetic field intensity, which we're just using as a proxy for how disturbed is the magnetic field, because you could get some false drift phase structure just because the magnetic field is rocking around and the particles may not be responding to it, but they're locked into it. And so we include that for comparison. But the real comparison we want to do is the flux to these gray limits that are shaded and they have a boundary on them. There are actually 2 different boundaries shown here. The one that's kind of ratty, it's actually a dotted line. Sorry, it's a dotted line, and it's a little bit outside the solid line edge. The edge defines the quasi-linear theory prediction for how large the drift phase structure should be. The dotted line also adds in Poisson effects, because sometimes you'll see drift phase structure simply because you have low count rates. We chose our events so that Poisson effect is very small most of the time. And so if you look at the rest of the plot, you can barely see those little dotted lines peeking out outside the bounds of the shaded region. But basically, as long as the orange and magenta curves are inside the shaded region, then we're within the quasi-linear. The quasi-linear approximation is a legitimate description of what's going on. We're not seeing large drift phase structures. I should also note that all of this stuff here falls within the delta L exclusion region. Just a moment. And so we will sometimes see weird stuff going on in that region, and we don't really want to try to draw too many conclusions from that region because the vehicle is moving so much faster. But there is one interesting place that happens in here, and the delta L exclusion happens to include the place where the radial gradient reverses. And when that happens, you get a 0 in the predicted size of the drift phase structure. Because if there's no radial gradient, then that offsetting that happens due to interactions with the electromagnetic field, it doesn't produce any change in phase space density. If there's no gradient and I take particles from a higher L and move them to a lower L, I can't tell. They're all the same particles. The only way we can tell there's been transport is by having a phase space density gradient that will highlight that transport has happened. So this is an example where the phase space, the flux is increasing over the course of 3 successive passes from the vehicle, and the drift phase structure is always within the bounds, except maybe in the L exclusion region where things start to fall apart because of the fast motion of the vehicle. Here's the whole event in the 4 passes that were selected for further analysis. And I should remind you that in this case, we're looking at DLL, radial diffusion coefficient computed from the Ozeki 2014 climatological model, which uses KP to determine the coefficients. We see in the first pass, which is a decreasing pass, that there is a little bit of drift phase structure following an injection that occurs, and you can even see that in the L profile. Unfortunately, we have a lot of the delta L exclusion region is rather large here, but even in that region, we don't see these drift phase structures here, which are those small waves in the orange and magenta. They're not large enough. They don't get outside the quasi-linear regime, even though they're actually not clearly not quasi-linear structures. They just aren't very large ones. That was the first pass, kind of near the main phase and the impulse. The second, or the pressure pulse. The second one we already looked at, and as I mentioned, that was an increasing case. And again, the orange and magenta curves are pretty much always inside the gray shaded region. The following pass here is pass C, and it's another case where we're seeing an increase from blue to orange to light blue. It's not as dramatic, but there is an increase going on. And unfortunately, I have a little data gap in the middle of it. But you can see that at some point we have a few cases here where the quasi-linear prediction of the size of these drift phase structures gets very, very small. The drift phase structures are also very, very small, but they do briefly peak out. And we may have a short case where that happens again toward the end. But even in this case, we're not seeing a lot of times where there's drift phase structures that are large compared to what quasi-linear theory would allow for. And the final pass is another increasing case, and it has, it has more observable drift phase structures in it, but they occur at times when the quasi-linear size is expected to be larger than that. So again, we're in the well within the quasi-linear regime almost all the time during this case. And here's another one of those examples where the phase space density gradient goes to 0, and you see that the size of the drift phase structure should go to 0. Okay, so now on the October 2013 event, I've got it all together on one giant slide. Hopefully it's not too small for everyone to read. This was this storm had a velocity and a significant velocity enhancement with it. It did not have the larger IMF of the previous case. It also had a good pressure pulse. We have all 4 channels reporting here, including the 2.2 MeV case. What we see is that the fluxes get changed during the course of the storm, but they kind of recover their pre-storm values afterwards. And I have 4 passes that I've picked out that are on the right-hand side. And then the KP value for this storm, again, gets a little bit above 5, but the DST is only about like -75, not as large a storm as the previous one, at least by that measure. In this case, we have the first example is a dropout where we have the pass we're in looks quite similar to the pass before it. That's the dark blue and the orange. And then the pass afterwards sees a really dramatic dropout. In that case, we have, again, we see that the detrended flux, that the 1 MeV detrended flux stays within the gray limits. We have another case of the limits going to 0. And we also look at the other energy channels. And although there's a bit more Poisson noise in this case, they're still looking very similar to the orange and magenta channel. So we're not seeing something that's only true at 1 MeV. It seems to be true over most of the range. I should note that this up here is in the red is more Poisson type, not drift phase structure. And then we look at the next pass, which is not an increase or a decrease. It's actually in the middle. The pass before was a little higher. The pass before was a lot higher. The pass after is a little higher. So it's a local minimum in the flux profile. And we see a lot more weird stuff going on because of the gradients here give rise to some larger structures in the other energies. But at the MeV energy, where we can really resolve things pretty well, we see drift phase structure. It's not very well correlated with what's going on in the magnetic field, and it's within the bounds predicted by quasi-linear theory. toward the end, it starts to creep out as we get to the lower and lower L. This pass is going downward in L. It starts to creep out, but that also corresponds to the L range where nothing's going on. As we see here below LF4, these fluxes are basically steady across all three passes. And that basically starts here in the time series, and everything to the right is in that period of not much going on. The next one is a case of an increasing flux. Again, dark blue, orange, light blue is the direction of time in these L profiles. And we see basically we're seeing the same story again. Fairly small structure in the particle fluxes compared to what we see in what we compute for the quasi-linear theory. And the final pass again is one of these with increasing fluxes. Really quite interesting feature of this storm is that things below L of 4 to 4.25 don't change very much. And I know there's some of you out there who always look at, how deep does this storm change things? And it really kind of hits a wall here at these energies, and then things below that are kind of untouched. But I don't know that you'd say that it's creating a sort of a storage ring type situation so much as it's just, it creates a shoulder, if anything. But again, we're not seeing a lot of cases of the flux getting outside the quasi-linear bounds, except here toward the end where we have some processing issues because we have a steep gradient and we're getting near the edge of our time window before we have to cut off and the vehicle start to turn around, go in the other direction. Here's the November 2013 event. We only have 3 passes in this one, and I chose passes that were all in the recovery phase. This particular event does have a modestly large negative BZ, and it's also got a solar wind speed increase, not much for a pressure pulse. DST gets up almost, like little around 5-ish. I mean, KP gets around 5-ish. DST, again, only about minus 75 nanotesla. In this case, we see a real increase in the particle flux from pre-storm values. By the time you get to pass C, everybody's up and enhanced, whereas beforehand there was, the belt didn't have a lot of content, especially at the higher energies. If we look at the individual passes, the first pass is a case where fluxes were decreasing and then sort of stabilizing through a lot of the outer zone. Unfortunately, the fluxes are kind of low, so we have a lot more of this fuzz, the Poisson noise fuzz, but that's part of why we chose the 1 MeV channel. It has a better geometric factor, and so it doesn't have quite so much of that. But we look here in our gray shaded region where the fluxes are consistent with quasi-linear theory, and the flux basically stays in that range almost the whole time, in spite of the fact that there are a couple of changes in the phase-space density gradient, which would narrows things down. We also see 1 or 2 cases here where changes in the magnetic field are kind of synced up with changes in the flux. Doesn't really change our conclusions, but it is. I was expecting, when I started this study, I expected to see a lot more of that, and we didn't really see that much. Okay, and then the next pass, things are increasing. So we have, at lower L, it's steadily increasing, but the timing is a little funky so that the current and previous passes line up above L of 5, but the next pass is the highest fluxes. So this is a period of increasing flux. And again, we do have some Poisson noise complicating things a bit, but we are still seeing that the MEV electron flux is largely staying within the quasi-linear limits, except toward the very end when, as I mentioned, we sort of run out. We're getting down to really low L and we're running out of counts. And we're hitting some edge effects on our windowed averaging. And so I don't know that we really need to, it's a short period of time anyway, but I'm not sure it's even telling us that at that time we're outside the quasi-linear limits. The last pass here is, again, the flux stays within the quasi-linear limits the whole time. And this is a case where we just experienced a flux increase and then it's staying stable towards the next pass. And, it's really quite flat. So that was a big tour of all of those. The next question we really wanted to answer, and this work's been going on for several years. And so in the middle of doing all this, we had event-specific DLL, but I think that the event-specific DLLs are getting more sophisticated. And so I think that this is going to be a good way to look at storms going on into the future. And people are also looking at like the statistics of DLL, which is helpful because the DLL doesn't necessarily stay the same for the 3-hour KP or for the time frames on which we can measure it. So just doing a time check here. Okay, so so in this case we have replaced the the climatological DLL in a couple cases from the June 2013 event. We've replaced the CLIMA with the event specific. And so we can look at it both ways. So in this case, on the top, this is the same plot I showed you before for this event. And then in the second panel, we're using the event-specific DLL instead of the quasi-linear DLL. And it's not really giving us a wildly different conclusion, except down here at fairly low L. Maybe we're seeing the event-specific DLL is smaller. And so the particle, the drift phase structure peaks out a little bit. And remember, this is the case where we're right after an injection or an impulse. And so I think that this is the case. This is, it's hard to be sure because we're going to get into the ratty edge of our where we can do our analysis, but it's at least the right place and time to see fluxes get outside the bounds, because you did just have an injection and that has led to these large drift pulses. But by the time you're at L of 4, the data are really well behaved, and you see that the fluxes, by the third drift echo, second or third drift echo, the fluxes are again within kind of what's already going on due to quasi-linear theory for a storm of that size. The next two plots show the same thing for a later pass, and in this case, we do have this L exclusion region, which is making things hard to understand. But outside of that, we have the climatological and the event specific. And the event specific DLL, everything from about 5 and above, they're the same. And then at lower L, you're seeing a little bit lower event specific DLL. But unfortunately, that's also the L exclusion region. Even allowing for that, where we're having large DL by dt, so some things are maybe a little hazy. Even then, we're really not seeing the fluxes get outside these somewhat smaller DLL limits or quasi-linear diffusion limits. So I think the conclusions still hold that while we do see drift phase structure, a lot of times it's pretty small, and even when it's not small, it rarely gets outside the bounds of what one would expect from quasi-linear theory. So the conclusion, unsurprisingly, is that quasi-linear theory is appropriate in all 3 of the storms that we studied. And that's because the drift phase structures rarely exceed the bounds computed from quasi-linear theory combined with the observed flux gradients. We see this both for the sort of 30% mag ice channels, which are the main channels, 30% delta E over E main channels, and the narrower 10% delta E over E histogram channel. And we also see it in climatological DLL as well as event-specific DLL. There are, of course, many caveats. I've highlighted 3 of them. We're looking at MEV electrons, and as the Chen result, and there was also a Riley and Wolf result, both of them showed that this is really energy dependent, where you kind of shift from the advective dominated or sort of the electric fields are pushing particles kind of thing, up to the diffusive mode where the wave fields are doing the pushing. And I should note that estimating the DLL from the wave fields requires several assumptions. So that's an area where maybe we've gotten it wrong, but I will say that the Ozeki paper in particular is quite thorough in looking at those and showing that different assumptions don't really make a dramatic impact on the DLL that they compute. And we were using the Sigonyenko 04 dynamic magnetic field model, which is a very good field model, but of course it's not perfect, and we don't have global field models. So we can't compute some of the parameters without some kind of field model. But it is at least possible that there are times when the magnetic field would cause the computation of MK and L to be a little bit more realistic, and therefore maybe that's an issue. I couldn't tell you how exactly that would affect our results, but it's always a concern. So the questions that this leaves in my mind, excuse me, are whether the wave power is more standing waves, which is kind of the picture that I showed you from Scott Elkington's illustrations, or traveling waves, which certainly for a soliton like the March 91 event is very much a traveling wave. but it's not really a wave, it's a soliton. I think we probably have some traveling waves, or traveling wave power anyway, that we need to look for. And that may be a significant source of transport. It's not as efficient necessarily as standing waves, which can resonate with a particle over successive drift orbits. But if there's a lot of that kind of power, then it's still going to dominate just because it's ubiquitous. I should note that broadband standing waves can produce resonant diffusion and over many cycles, and it can be inherently diffusive. So that's not a problem. That doesn't make an issue for quasi-linear theory, but I think it's important for us to understand how to think about the wave power. Is it standing or traveling waves? Because that does sort of change how we relate our magnetic field and wave models to the particles. The DLLs, for example, were computed on standing wave assumptions. But traveling waves can also produce quasi-resonant transport, because they're traveling waves, they are much more disorganized, I suspect, and it's easier for them to produce diffusion because they're more random. Just a moment, I got some water here. Okay, so in the future, I need someone to help me because I don't know how to do this myself, but I believe our MHD models can capture much of the ULF wave phenomena that leads to radial transport. And so while it may not be exactly what happened in any one storm, it is a realistic representation of ULF wave motion through the magnetosphere. So I think we could use those wave fields to test whether the waves are primarily standing or traveling waves. And my scheme for doing that, with some partner out there who can run an MHD model and analyze it, is to narrowband filter the MHD simulation fields and then make a quiver plot of what direction the pointing vectors are in. Because I'm pretty sure that wave theory tells us exactly what the pointing vector should be for standing waves. And if it's not that, then it's probably traveling waves. And it might be interesting traveling waves. They're all going, say, downtail or something like that. So I'm hoping that doing that would help us understand whether the power at various frequencies is organized in sort of the standing modal structure, or it's just a superposition of traveling waves on their way downtail or across the magnetosphere or wherever they're going. But there is one caveat to all this, and that is that the ring current plays some role in ULF wave propagation and maybe generation and absorption. So we need to look closely at these coupled MHD ring current models to see if they can faithfully represent the ULF waves better than the MHD models alone. And work is going on in that across the community, but I think it'd be a particularly important issue to look at in a study like the one I'm proposing, just because it's probably important. If you go down to the lower L's, you've got to account for the ring current more. And that's all I've got. So thank you for listening. And I guess Dave or Kyle, one of you can tell me what we do next.
Next, you get some questions, but first we say thank you. Very clear. You're on time. Everything's good. So this was a wonderful presentation. Catch your breath for a minute, and I am going to read the questions as they appeared. You may have answered them in part subsequently, but we'll give everyone a chance this way. Lynn Wilson is curious to know whether you consider solitons to be waves or not.
I would say that they are, in many of the ways that we think about waves, they are waves because they move like waves. But there is some clarification is required because they're not repeating. And so they don't have when they interact with particles, they don't have quite the same behavior. They're more like a travel time resonance than a recurring drift resonance. So we have to keep clear in our minds that they're essentially a wave train of one.
Yep. Okay, thank you. Next question. Mike Henderson would like to know, how do you separate L from L star in this analysis?
We always use L star for our, when we're computing our gradients. I think this plot here may be using L, McElwain L. I don't know that that makes any difference, but I believe that is the case. And then here, we're using a dipole L because this is we're computing drift periods analytically from the formulas for a dipole. So where it's really important, we use the L star, but in other cases where it is more convenient or more conventional, we use McElwain L or a dipole L.
Okay, thank you. Biswajit Ojha would like to go to slide 9. And his question is, when you're talking about measuring drift phase structure from in situ data, do you expect a critical relative velocity of the spacecraft with respect to these structures? Does the spacecraft velocity matter?
So in these cases, the only way that we look at the spacecraft velocity is the radial motion. If dl by dt is too fast, I think that when you're talking about the motion, the speed of these are MeV electrons, so their motion relative to the spacecraft is very, very fast. Even their drift motion is fast compared to the spacecraft motion. But when you get down to perigee for this vehicle, you might need to think about it. But at these, we're primarily looking in the outer zone where the spacecraft isn't moving very fast, and we don't consider its velocity as part of the calculation.
Okay, thank you. Now, J. Albert asks, you say drift phase structure, but aren't you really looking at drift average radial structure?
Good point. So we use the drift averaging to separate out the drift average phase-space density with respect to M, K, and L. And then that's how we compute all of our gradients. We then subtract that drift averaged structure or drift averaged flux from the high time resolution measurements that aren't averaged to isolate the drift phase structure. So we do use both drift average for computing the gradients and then the residual after removing that drift average for identifying the drift phase structure.
Okay. Now, Eric Lund would like to know, how do you get a non-contiguous L exclusion zone, as in pass C, in the June 2013 event?
Pass C here. Yeah, so this is because of the, we're using the Sigonyenko field models, and as the field changes over the course of the storm, you can get that. It's because what's happening is it's dl by dt at the spacecraft, and so if the magnetic field is changing a lot, then you can get dl by dt that's caused not by spacecraft motion but by the magnetosphere reconfiguring.
Understand. J. Albert came back with another question. Can you distinguish your chosen DLL being inaccurate from no version of DLL being sufficient?
Well, we did not look at multiple versions of DLL. However, they do tend to show each other that, that they're in relatively good agreement most of the time. And so I think that's not the critical point. But what would make this an issue is if the Ozeki DLLs were systematically quite a lot larger than the others. And I don't think that's the case.
Okay. Next question. Lynn Wilson asked, aren't many waves in the radiation belts and magnetosphere intrinsically kinetic? That is, can MHD actually handle these modes?
So that's where we need to talk to the ring current models. Certainly, I think some of our ULF pulsations are and ought to be well described in a pure MHD, but I think that it's enough of an issue, particularly when you're talking about getting down to the lower end of the outer belt. You start to need to be more concerned with it. And so in my opinion, we should be moving towards incorporating that aspect of these waves. Even though I think our approximations now are certainly good enough for the kinds of studies we're doing, we need to do better to kind of pound that doubt down a little bit more.
Okie dokie. And the last question, at least the last one that I can see, is from Kyle Murphy. It begins with a comment. He thinks this is a very cool and complex analysis here. He wonders if it's possible to automate the analysis for statistical study. How did you choose your intervals? Was it based on data availability and quality?
Yes, it was mostly due to availability and quality. The unfortunate reality is that the MagEye sensor is a bit small, meaning its geometric factor is a bit small. And so finding events where interesting things are happening and you have good data where you don't lose your drift phase structure in Poisson noise, that did prove to be a bit of a challenge. But we also, as you noted, all of our maybe I don't know who noted it, but our events are all fairly early in the Van Allen probe mission because that's what we had when we started doing this study. We could revisit it, and I think there would be more cases to look at. As far as automating it, a large amount of this can be automated. There is the part that you can't automate is the really more of the quality control. And that even some of that could possibly also be automated. I haven't tried to do it, but most of the parts that are not automatable tend to be like identifying the pass boundaries that you want to focus in on, because you don't necessarily use the whole pass, for example, because the L value can start to ripple when you're out at the highest L. And so some cleanliness issues like that, nothing really challenging. And so it would be probably not too hard to expand this to a larger interval of time. Trying to do the whole Van Allen probe mission could get very labor intensive. But if you're focused on that, maybe you could automate some of those quality control issues as well, and then only choose the highest quality events using some metric. And then you could maybe get, dozens or more.
Okay. There being no further questions, I'd like to thank you for a spectacularly interesting, understandable, and enjoyable talk. I'd like to thank everyone for attending and their good questions, and we'll see you all next week. Thanks very much.